Okay, today, as expected, not many people showed up. So we are approaching like the end of the course. Um, I think we have. I will try to cover today some. We are going to talk today about flow assurance, a bit about multi-phase flow, and then we will have hopefully from next week some sessions in the computer lab. We are going to talk about. I just want to give you a taste. You won't be, professionals working on the software, but working on Prosper and Gap that you can use for making calculations of production rates. And hopefully, let's see if we have time to go through LedaFlow. Remember the software? You had a guest lecture some weeks ago. So let's see, and then you will have an exercise on that. The last exercise. So there will be not five like we originally planned, but only four exercise sets. Yeah, and the last one will be when all the lectures are finished. But we will try that from now on, from next week, all the lectures will be in the computer room. It will be there in P2. I hope we have, there is. I hope that we can do it. Okay, so we talked just to refresh your memory and my memory also. We talked about gas. We talked about oil, okay, or what we say like slightly compressible liquid. And I want just to give you now just a very short orientation about what we do when we have multiphase. Okay, multiphase is a bit more complex, but you will see some similarities of what the stepwise type calculation that we have been discussing before. So I will call it flow um, equilibrium. Okay, pressure drop calculations with multiphase flow. Okay, and multiphase flow basically we are saying if we are talking about oil, okay, if we have the PT diagram, okay, remember in the reservoir usually if it's undersaturated we are someplace here, but when we flow through the separator conditions, let's say that P separator is someplace here, you will have that the temperature decreases and also the pressure decreases. So up to here we can use all the equations that you saw, all the single phase equations, but from this point down you'll have multi-phase flow, and you will see it on the wellbore. If we see our famous well, let's make it here the casing. So we put a packer. Okay, you will see first that we have everything is just when we are at this point 1. Okay, everything is just single phase oil. And then you will start having some, after I cross that point, you will start having some bubbles of gas. Okay, we can put maybe a number. We can say 1, that will be 2. And then after we go a bit further down, then these bubbles will start to get bigger, either by coalescing themselves, two bubbles are merging into one bigger bubble, or also you're getting more gas coming out of solution. So you start getting some bigger blobs, okay? Not anymore this flow pattern, we call it, this one we call it, the way, we see the phases are arranged, in this case the oil and the gas, that's what we say is the flow pattern. Okay, and this one we call it bubble flow or bubbly flow. This one, when the droplet starts to get bigger, Okay, it's still like a bubble flow, but more like a churn type. You have some bigger structures. Then you have some very nice, like a slug type. So this one we call it slug flow, where we have batches of liquid. So that, let me see, we forgot to put the numbers. So that will be 3, that will be 4. 3 someplace here, 4 someplace here. Okay, and you can even go to the other end, such that if you have too much gas coming out of solution, the gas will start to occupy a very big volume. So then you will have just gas will be the main core, and then you have liquid that is basically in droplets, like a mist in the gas, and the liquid is going on the walls. Okay, that's the extreme. Usually we get only up to slug flow on wells and transportation lines, but you can also have this type mist type annular flow. Okay, let me put a number 5 someplace here. Okay, that's slug flow, that's bubble churn flow, and that we call annular flow. Okay, and we can have all of them in one wellbore, and that's part of the complexity of performing multi-phase calculations. Okay, before we were saying, well, everything is like that. The only thing I have to change is the rate, right? But now you have that along a conduit that you want to make your calculations. Let's see this, yeah, recording. You will have different flow patterns, different distributions of how the flow is arranged. So, you have still, it's even more important to make this discretized calculation type. You stand here, you calculate one step up, then you stand here, you calculate one step up, and so forth. Also the same thing, so that's for oil, an oil well. Okay, but you can also have it for a gas well. Exactly the same thing. But gas, if we exactly, it's not exactly the same, the diagram, but gas, remember, we usually come from here and we go down here. Okay, maybe that will be again P separator. Gas well. Okay, so initially we have just pure gas flowing, that the equations that you learned and you have been using, they apply very well. Okay, then you start having some droplets. You start that they condense out of the gas. You start having some droplets of liquid, and this usually is what we call mist flow.
Right, the gas and green liquid.
This is gas, and then you have that the first droplets, when you start crossing here, that will be number 2. Okay, that will be 1. 1 will be here, all of these range, and number 2 will be exactly when you are crossing the line. Okay, you start getting the first droplets condensed out of the gas, and then you start again the same procedure, the same that you have this annular flow. All the liquid, when it starts getting enough quantities, they start accumulating at the wall, and you have more droplets like transported in the center. And then you have that these liquids will start getting like some blobs. You have some sort of a churn type flow. Okay, and then ultimately you get exactly the same pattern that you had, which is a slug. Okay, and of course, there are some cases where you don't have all of them in a system, some cases where you have all of them, but that's a general picture. Okay, that's how it looks like what we have on the flowing well, and also in the transportation line. So I'm not going to talk here about too much about multi-phase flow. For that, I want to make here, if you have more interest, if you are interested on multi-phase flow, okay, recommend you to take the course that we are sharing, these guest lectures with that course called TEP 4250 as a professor called Ole Jørgen Nidal. Okay, and then you can get um, more information if you are really passionate about multi-phase flow. Okay, but our main task is to, like before, is to calculate delta P along a conduit. Okay, and we are going to see later today why also temperature we have been taking it a bit, not considering too much, but we will see why that's important just in a while. Along a conduit, okay, either along the well, tubing, pipeline, flow line, etc. Okay, just we want to make this equilibrium. Okay, that's the principle how we calculate rates. But again, due to that, so that's the purpose. Okay, we can say that's the purpose. Compute delta P along a conduit, but due to the variation in flow pattern, okay, I have to perform it in a discretized manner. Okay, I have to stand in one place in the pipe, and then I have to, from that place, I have to calculate the next one, and so forth. And I'm going to give you a small orientation how that's done, at least that you get the picture a little bit. Okay. That part, I don't think. Okay, so let me put like a cookbook. Okay, I'm going to put it like a recipe. Okay, the series of steps that might be slightly different, but usually they are like that. Okay, so I say depart from a point with known pressure and temperature. Okay, a point where I know what is the pressure and temperature. If I don't know, I assume. Okay, if I have, for example, like in all of our cases that we have been studying, we have a well. Okay, if we have, let's say we have a separator very close, right? We can say, well, that well is operating with a constant wellhead pressure. If that separator is is far away, then I have to assume, because the pressure I don't have it yet, or I go from the separator upstream. Okay, that might be an option. But I depart from a point with known pressure and temperature. If I know, for example, this pressure, then I move co-current, or if I know that pressure, I move counter current. Okay, just exactly like we have done before. Then, um, then I have, if remember, I need to have like what we have done before. Okay, I need to assume either assume the operational rate. Okay, So the second is assume a rate. Okay, if we are in an oil, we assume oil. If we are gas, we assume gas. And with GOR and water cut, we calculate the rest. Okay, we calculate the gas and we calculate the water. After I have that, okay, I actually have the, remember, for gas, either for gas or for liquid, what causes the pressure drop is actually not the standard condition rate, but the local condition rate. Okay, that's what causes the friction in the pipe. So it's exactly the same thing, and I have to calculate those rates. Okay, I have to calculate the local rates. So I have to calculate local rates, and I have to calculate also the fluid properties. And for that, usually there are two main ways to do it. One of them is using black oil properties. If you remember, maybe we defined them before, but we had that BO, we have all of these BO, BG, RS, and small rs. Okay, we have all of those properties that they relate properties. Let me, all of you are clear, or do I have to go through black oil properties? No, you don't know. Okay, black oil is an approach that we use to say if we have certain oil, a certain gas at local pressure and temperature. So here we have a volume of gas and volume of oil. Okay, then I go and I take those volumes, I take it through a surface process. Okay, can be any surface process, can be a sequence of separators, can be one single stage. I can take it straight to standard conditions, and from the gas, if I take the gas through that process, I'm going to get a standard condition volume of gas that comes from the gas. Okay, so I will call it BG coming from gas, and here I have oil that comes from also from the gas, that condensated from the gas. Oil, standard conditions oil that came from the gas. And also the same thing will happen with the oil. You will have a volume, big volume of gas, standard conditions of gas that came from the oil, and you have also some oil that came from the oil. Okay, that clear? When you pass it through a process, any process can be, you just pass it, flash it directly to standard conditions. It goes through a series of separators, it goes through a plant, a processing plant, it goes through anything, you will have that process. Okay, so then you can define that BO will be volume of oil divided by volume of oil from the oil. Okay, you can define that BG it's volume of gas divided by volume of gas from the gas. The RS will be volume of gas from the oil divided by volume of oil from the oil, and the small rs will be volume of divided by BGG. That correct? Yes? You're checking if you're awake. I hope I didn't make any mistake. Let's check it once more. Okay. So that's how we can convert. If you see, if we use this BO and BG, we can convert between standard conditions and local conditions. If we have local rates, then we have standard rates. But we have to make a distinction between where is the oil and the gas coming from. That's why we have this additional complexity of this small RS. In the traditional black oil approach, we don't have this RS. We just have a big RS, and we actually don't take care into what oil comes from the gas, condensed from the gas. And that's an approximation good enough for heavy and for not so light oils, but for light oils and condensates, we actually have to take that RS into account. So I'm just going to put the formulation here, the general formulation, and then depending on the case, you might not, consider RS. But then we have that actually the rates, we can express a matrix, okay, the local rates at any pressure and temperature just will be equal to a matrix which is made by these black oil properties. Okay, we are assuming that there is no water absorbed by the gas or any water in the oil. Then that will be at a certain P and T, okay, and times the this will be gas, this will be oil, and this will be water. Okay, just that transformation. Okay, so what you have to have is to compute that matrix for any given pressure and temperature. That you do by calculating these black oil properties, and then you transform. If you have these rates that in this case we are assuming, right, you are transforming from standard conditions to local conditions right away. And this is a method which is very effective. If you have these, for example, computed in tables, you don't have to be computing them at all. And then that's a very straightforward process. It's just an algebraic multiplication of matrices. Okay. Yes, I think that's correct. So black oil properties come from, okay, they come sometimes from measured data, okay, from laboratory data. Let's put it better that way. Lab data. Okay, then, or you can use black oil correlations. Okay, the correlations were made for fluids from, they take a fluid from certain area, oil from the North Sea, oil from California, and they try to make a correlation for all of those properties. And if your oil fits very well with that, or your gas fits very well with those properties, then you can use it. Or you can also generate from an equation of state. Okay. And why if you already have an equation of state, why you still use black oil properties? Just because it's much faster. Okay. Remember EOS, if you took the course with Professor Whitson, it's a long process. You have to fugacities, estimate Rutherford Rice, etc. So it's a very time-consuming process. If you use this approach, they are already pre-computed in tables, and you just go. It's a very efficient process. Okay, the other approach we have to calculate local rates is using an equation of state. And I'm going to bring that to the next page. Sorry. Okay, an equation of state. And the equation of state, the first step is I have to calculate the total mass flow rate. And that I can make by, we already covered a bit about that before, but I say Q oil mass rate will be equal to the Q oil times the density of the oil at standard conditions plus Q of the gas times the density of the gas at standard conditions. And if you have water, well, it's the same. Okay. And after I have that, then I need to have a composition of the fluid, which in some cases is a problem. Okay, the composition can change from one day to another, and I have to have the composition for that particular. So I need the composition. Okay, that we call with set I. We need the molar fraction of each component: C1, C2, C3, CO2, etc. All the components that are on the stream. Then when I have that, I actually perform a flash calculation at that particular pressure and temperature. At P and T. And from there I calculate all the things that I need actually. I calculate from there the density of the gas, the density of the oil, the density of the water. I need the viscosity of the gas, the viscosity of the oil, surface interfacial tension, oil and gas, interfacial tension, oil and water, interfacial tension of gas, water and gas. What else am I missing? Okay, nothing else, I think. And most important, we calculate from here the mass fraction. Okay, we calculate from here the mass fraction of the gas. Here is mass fraction of the gas, okay, which is simply m xg. Sorry, make it a bit nicer. mg divided by mg plus m oil, okay, or m liquid. With that, I can calculate mg and m oil. Okay. After that, I can calculate the Q of gas will be equal to mg divided by the density of the gas, and Q oil will be m oil divided by the density of oil. And after I have that, finally I reach the same point as the black oil approach. Okay, for black oil I also have correlations for all the other parameters. Okay, I have correlations for, I have also density of oil at pressure and temperature. I have density of gas, pressure and temperature. I have interfacial tension of oil gas, interfacial tension of oil and water, and interfacial tension of water and gas. Okay, I have correlation for all of them. And finally, I reach the same point. But I have to make this flash calculation, and I need to have a composition, okay, which sometimes it might be, difficult to get it. Okay, but after I have that, I have my rates. Then comes the most important step, which is I have all of that information. So that was the step. Which one? Remember, we said known pressure and temperature. I assume a rate, and then I calculate local rates and fluid properties. And then comes the fourth step, which I calculate dP over dx, okay, at that point, at that position, okay, in the pipe, in the well, whatever, okay, and that you make, so that I use all of these properties that I said before. Yeah, here I don't want to go too much into details, but basically I use densities, viscosities, surface interfacial tension, and then the most important, I use the superficial velocity of liquid and the superficial velocity of gas. That's nothing more than the Q of the liquid divided by, or the oil divided by the cross-section area of the pipe, and the Q of the gas divided by the cross-section area of the pipe. And I need also the pipe diameter. I need the inclination, pipe inclination, and I need the roughness of the pipe. Let's see if I have everything. Yep. And why is that? Because as I told you before, you have all of these flow patterns developing in the well. Okay, you have that it can be bubble, it can be slug, it can be annular, etc. But which flow pattern you have actually depends on all of these inputs up to some way or another. Okay, if you have, and basically it depends mainly on these two guys: superficial velocities of gas. If you have too much gas, okay, and little liquid, then you will be in an annular flow type regime. Okay, you will be probably here. If you have a lot of gas and a little bit of liquid. Okay, if you have a little bit of gas and a lot of liquid, you are probably going to be in that regime. So that's the main or the most important factor. Okay, these two guys that I have here, the superficial velocities, but also depends on all the other properties, densities, viscosities. The inclination of the pipe is not the same if the pipe is horizontal or if it's vertical. So it depends on all of that input, and I'm not going to go too much in detail there. But basically, you can use, there are different approaches, but you can use correlation. Okay, people try to make, based on all of that input, try to make a correlation for delta P. I can use what I call a mechanistic model, where I try to make a force balance and see which flow pattern is the most likely. Okay, is the most is most likely. Or I can use some simplified models, just like the homogeneous model, or for example the drift flux model. Okay, where I just assume that, well, the delta P is basically similar to the delta P in G. I need here D set, or D, yeah, D set. Okay, where I basically try to approximate that mixture with a density of the mixture, and also a velocity of the mixture, and a friction factor of the mixture. Okay, but we are not going to talk. So at that point, you just say you have to calculate the delta P, and for that you can use any of these methods. You can use an expert. You have someone that knows how to compute the delta P. And after you do that, number 5 is that you integrate and find the pressure for I plus 1, okay, for the next point in the pipe. If you are departing, let's say, from the wellhead, you have P wellhead, and you want to calculate that pressure here. Okay, let's call that I plus 1, is I plus 2. Okay, you move stepwise and you calculate what will be the pressure there. And basically, that's solving at that particular point, just a differential equation. Okay, that you have dp dx is a constant, a number, and you have that p at x equals 0 will be pwh. Okay, and you want to calculate what will be p at I plus 1. And you can do that by different approaches. Maybe something that you saw when you were in school, kindergarten. You have Euler's method, which is very simple. Euler's method, you'd say that pi plus 1 is pwh minus dp dx times delta x, the separation between these 2 points. You have other more complicated. You have predictor, corrector. You have Runge-Kutta. You have all kind of methods that you can use, but that's simple Euler. Okay, you have implicit or other implicit and explicit methods. Okay. And after I calculate the next point, I have now a new pressure, I have now a new temperature, and then I go back to point 1 to point to point 1. I don't need to, as I have already the rate, I go to step 3 and so forth. Okay, and I repeat for the next point and the next point and the next point. Okay.
So how can you calculate the new temperature?
We are going to go to that, but for now assume that we say, let's say for this particular case, we say it's similar to the geothermal gradient. Okay, let's say that for that. For that, now temperature is an input. We are going to go to that, but just maybe not today. I'm going very slow today, so okay, that clear? So the main point is that it's a very time-consuming process. To make that calculation stepwise is very time-consuming. You have to call, if you're doing compositional, you have to do that, an EOS. If you have to call your multiphase expert, that sometimes is very simple, it's just an equation. Sometimes it's a mechanistic model, something that you may have to iterate. So it's a time-consuming process, okay? Okay, just that to be, and what I say is that, for example, right, if you have, here you have PWF versus Q of oil, okay, and let's say you have the IPR, you have one equation that looks like that, and then you are repeating that calculation, you assume a rate, that will be PWH constant, right, and you assume this rate, and you calculate this bottom hole pressure. Then you assume another rate, and then you calculate this bottom hole pressure, and then another rate, and so forth. And if you remember the curve, I told you it looks something like that, right? The available pressure, the required pressure at the bottom of the well, and that's the available pressure. And for each one of these points, you had to make that integration process. Okay, for each one of these points, you had to go from wellhead all the way to bottom hole to calculate the flow pattern in each one of them, calculate delta P until you reach here, and that's the point you're plotting here. That's extremely important. Okay, each one of these points, it takes a lot of effort to calculate. And yeah, so why the curve looks like looks like that. Here is very clear, right? Exactly what we had for the single phase case. When we increase rate, what we are doing is just we are increasing the frictional part of the pressure drop, right? When we increase the rate. But what is happening here from 1 to 2? Okay, a very simplistic explanation is that if we have the pipe, let's assume a vertical pipe. Okay, initially we have some gas and liquid, right? But the velocities are so slow that the liquid is almost stagnated. Okay, the liquid is almost like going slowly up. And because of that, the gas is flowing very quickly. Okay, and basically the cross section, if you see here the cross section, if we look at this piece, okay, the density of the mixture will be very close to the density of the oil. Okay, not at standard conditions, but local. It will be very close because the gas is flowing fast, so it doesn't need really a very big cross section to flow. It's flowing through a very small section. Thus, the density of the fluid in the density of that pipe section will be very close to the density of the oil. Okay, after the velocities, that will be in point 1. Now in point 2, what happens is that the velocity starts to increase, okay? Overall, the velocities of both the gas and the oil. So if you see just at the oil here, if we take just the oil part, what is really helping the oil to flow is the shear that the gas makes on that face. Okay, you have here some force, or let's call it, shear force, we can call it tau, okay, that is helping or dragging the liquid up. When the velocity, overall velocity increases, that has a higher effect. Thus, the liquid starts to flow quicker. Thus, if the fluid and the gas is slowed down, okay, it goes a bit slower. So because of that, the cross section occupied by the liquid becomes smaller, and the cross section occupied by the gas becomes bigger. Okay, here I'm just exaggerating, but that's what happens. Okay, and here the density of the mixture will be something between density of the gas and the density of the oil, something in between. And because of that reduction in density, well, we have also a reduction in the pressure drop, in the pressure that we require. If we increase it too much, then ultimately we just have the friction part will be much, much higher. Okay, but that's, so it's part of the mechanics of the dynamics of the two phases flowing together. Okay, so now if you understood that, I hope that you did. Okay, the way we work with multiphase flow is that we pre-compute. So pressure drop in multiphase flow is typically pre-computed and stored in tubing in tables. Okay, I'm not going to call it tubing, but in flow, what we call flow tables. Because of that process, right, we need to have access to this expert, we need to have access to properties, we need to have access, and that might be a hassle. The way we make it is that we pre-compute, we take that and we pre-compute a lot of conditions, okay? So we say, for example, the way the table looks like is I fix wellhead pressure, okay, P wellhead pressure 1, and then I calculate for different rates Q oil, okay, and here is also water cut 1, and GOR equal to GOR1. Okay, and I make a table that will give me PWF, QO1, QO2, QO3, QO4, QO5, okay, and all the PWF1, PWF2, okay, 5. Okay, and here of course I have, that's oil at local, and here I have Q gas, it's also reported, and here I have Q water, and also I might have the temperature of the wellhead, okay, for all of these cases. But this, what is going to give me essentially is Q oil is exactly those points in the curve, okay. It's going to give me that curve that I plotted before continuously, but it's going to give me several points in the curve, okay. And in that case, then after I forget about that, if these conditions are not going to change, I just take the collection of points. I just take that table as a proper representation of the performance of that pipe. Okay, instead of having to run live calculations every time, I just take the collection of points and I forget about it. So for example, if I have an IPR, okay, to make the intersection, another trick that is also made, I also convert IPR in a series of points, okay, that you will see next week when we talk about Prosper, when we go a bit about in Prosper. And then to calculate the intersection, you don't have to be using solver, you don't have to be using anything, you just make intersection between two straight lines, which is very simple, okay, it's one equation that you can write very easily, okay, and that interpolation and intersection is very cheap, is very fast, and is very friendly for many types of simulator. Okay, you can use it in reservoir, you can use it for your production profile calculations, you can use it for many things. Okay, so that's the way we deal with it. We pre-compute a series of conditions. Okay, now be aware. Okay, for example, let's say if the IPR is like that, right, and you calculated my points, let's say that this is Q04. Okay, actually the intersection will be to the right, and I don't have enough points for that, so I can make either an extrapolation, but the better case is that I make more points that are higher than Q04. Okay, and sometimes for some cases you're not sure, which rate the well will be producing. Okay, so that's something that you have to be careful. Also, another thing is that usually, or there are some cases, not usually, but let's say there are some situations. We are going just now on a break, just wait a moment. There are some situations where PWH is not known a priori. Okay, for example, if you have that system that I told you before, there you have a separator, you have a long pipe, and then you have the wellhead. Okay, in that case you don't know what is the pressure before you make the intersection. Okay, so you have to make to make runs to perform calculations for different for P wellhead 1, P wellhead 2, because I'm not sure, and I have to assume, and I have to have another table for the pipe, and I have to make the intersection, see which will be my operational point. Also, during the life of the field, the life of the well, then water cut will change, and the GOR usually also change. So I have to perform calculations for GOR1, GOR2, GOR3, GOR4, etc. and water cut 1, water cut 2, water cut 3, water cut 4, and so forth. Okay, so I have to make, so the point being that I have to repeat that table. Okay, if I copy that, and here just don't type because you won't manage to catch up with me. That will be water cut 1, and put it to the left. Okay, I have to make one more. That will be number 2. Okay, now just changing the wellhead pressure, keeping everything else the same. 3, 4. Okay, and now after that's done, I have to make the change on water cut. So I again come, again the same thing, and then I put water cut 2, water cut 3, water cut 4. Okay, and then I have to make it on the GOR 1, 2, 3, and then I have to do it for all. So it will be the combination of all of them. So if the number of runs, okay, number of runs to make, okay, in the simulator, actually it's the number of rates that I have times the number of wellhead pressures that I have times the number of GORs that I have times the number of water cuts that I have. Yeah, these numbers, they can change, but usually we use numbers around maybe 5 to 10 for all of them. So if we assume 10, here we will have something in the order of 10 to the fourth. Okay, 10,000 iterations we have to make to compute these tables. Okay. The good thing is that after I make once these calculations, once these 10,000 iterations that you're going to make next week, then I don't have to worry anymore about pressure dropping the pipe, about anything. I just can forget about everything else, all the previous steps, and I can just use the tables. Okay. Any question before we go to a break? No? Okay, that's all I want to say. That's all I want to talk about a multi-phase flow. Okay, we are going now to talk about flow assurance, but that's that, and we are going actually to use the software. Just so I want just to make you aware when we are using the software. Okay, so let's take a break, 10 minutes, and then we come back. Yeah, so that's the point here. The main conclusion is to just to show you how calculations in multi-phase flow are performed. They are extremely sometimes they match perfectly, sometimes they don't match. You might have deviations of 30% are normal. Okay, so that gives you, when predicting production profiles, the flow performance of the production system, that can give you a very big variation that you have to take into account. So always, your model that you use here, you have to be sure that is matched with your data that you measure. Okay, you usually have wellhead pressure, for example, separator pressure across a pipe, so you can use that just to improve your model, or to try to tune your model to your data that you have. But it's a time-consuming process, so we prefer usually to work with it like a table, okay, like a pipe. We pre-compute a lot of conditions, and this is a heavy process. It takes time, but after, we don't have to worry unless we change the tubing, unless we change the fluid type, unless we, something else happens. Okay, but we don't have to change. So now in the second part of this lecture, I want to go very quickly through flow assurance issues, okay, that have to be considered. And luckily, you already have some lectures, okay, on these issues, so I don't have to talk too much myself about them. But I just want to make a summary table. Remember, flow assurance, it's a term saying that everything that impedes the normal flow or production of my hydrocarbons from the reservoir, from the source rock, all the way to from the source to the facilities. Okay, and we have basically, I can say, three different effects. Okay, one of them is increased delta P, okay, which will give me less production because the intersection is going to be moved. Okay, flow restriction, and ultimately it can lead to blockage. Okay, that's one effect. Okay, the second is integrity problems. Okay, for example, a hole in a pipe, a leakage, something that you have a problem with the integrity of the component. And then the third one is loss in functionality of components. Okay, that, for example, a valve that it gets clogged, that it cannot close or cannot open. Okay, so these are three effects that these issues cause. So I want to make just very quickly a summary table where I'm going to put here flow assurance issue. Okay, I'm going to put here the consequence, okay, according to the table we have defined above, and here I'm going to put the corrective measures. Okay, so first, let's go talk about the ones that we have discussed before. Wax. Okay, consequence is basically mainly number one. Okay, that you can cause remember the cross section of the pipe is reduced. You have this precipitation and deposition of wax on the pipe wall that you have an exercise on that. And that's due because the temperature is reduced below certain level. These alkanes, long alkanes chain start to precipitate out of the oil. And that can cause increased delta P, flow restriction, and ultimately lead to blockage. Okay, what corrective measures can we take? Okay, pigging. We can also insulation, extremely important for the field development process, that you have to define how much you have to insulate the pipe. Then you can also put some external power source to heat the fluid, heat tracing. Okay, what else do we have? And here we have with pigging, we have the pigging loop requirement. Okay, remember, if we don't have a place where we can send and receive the pig, we have to make it round. Okay, we have to make it the same place you receive and take, and that's also very expensive. And we have also some chemical inhibitors. Okay, that they work, but sometimes you need high quantity. They are expensive and they are not. Okay, and if we are going to inject an inhibitor, this one at the same time affects the chemical injection system. I need to have something to deliver that chemical, so I need the chemical injection system. Okay, so that's our first problem. What was the second problem the guest lecturers covered? Hydrate. Okay, what hydrate? What does it cause? Okay, it causes number 1 basically, and can lead to number 3. Okay, and what can I do to avoid hydrates? Okay, basically I can use inhibitor. Okay, that also affects my field development, that I have to have a chemical injection system. Okay, if I need an inhibitor, I need to inject it where it's needed, usually after the wellhead, so I need to have a system to inject this chemical. Okay, then I have some other measures. I can use insulation to avoid that the temperature will go down, or I can use a heat tracing, basically to try to keep the temperature above the hydrate formation temperature. Again, I have some other things that they talk that they're not really that much use. I can use an inhibitor, but kinetic inhibitor, but basically injecting a chemical. The third problem that they talked was if you remember, was asphaltenes, right? Okay, asphaltenes can also lead to blockage, can lead also to loss in functionality. And what kind of measures do we have for asphaltenes? You were asleep? Yeah, chemicals. Okay, they say that actually we have to know that they are there, and we have to, but basically I can use some chemical inhibitor, but I need, at the end, I need some kind of mechanical removal. Okay, chemical inhibitor, not only inhibitor, but they use chemical removal. Okay, that are these how do you call these, resins? Okay, what else do we have that we cover here in class? Emulsion, right? Like, what can cause emulsion? Emulsion basically is only number 1, right? And well, it can cause also some number 3, okay, loss in functionality, like in the separator, in the top side separator. If I have a very stable emulsion, then that separator is not going to separate as fast as we expect, and then you have a loss of functionality. Okay, so let me put that comment here, that in top side separation. Okay, how do I deal with emotion? Chemicals. Okay, for everything we give a pill and that's all. You're going to get better. We are like doctors, but let's. So we have some demulsifiers. Okay, that they have. Just be aware. Sometimes they work. Okay, sometimes they have some effect in the interfacial physics, interfacial phenomena, and sometimes they can make it less stable, the emotion. But sometimes they have limited effect. Okay, depends the shear, depends on the characteristics of the fluid, but it in truly it's a chemical that we inject to to maybe reduce the peak, maybe disappear the peak to try to make the emulsion less stable, to promote separation. What else do we have? Okay, some other things that we haven't covered. We have scale. Okay, what scale can cause what? Number 1 and number 3. Okay, in increased pressure drop, the cross section, you have minerals, you have that precipitate out of solution, and they also accumulate or deposit on the pipe wall, and also different components. They might be caused for different things, changes in pressure, but also mixing waters from different sources. Okay, if you are mixing water from produced water from the formation and from injection water. Okay, then the solubility of these all of these minerals, they change and they can cause to precipitate. What do we do for scale? Inhibitor. Okay, again chemical. Okay, scale inhibitor. Extremely important. Some cases I have a huge accumulation. The well can get plugged very quickly. Okay, and what else do we have? And here I have also mechanical removal. Okay, I come with a reaming tool and I try to open, to clean whatever scale is accumulated. There are some scales that that's the only way that I can remove. And also it has scale remover. Okay, if a scale is already in place, I can inject the substance to remove the scale depending on the type. Okay, and then we have many different things, but I want to call just two more. Erosion. What can erosion cause? Number 2, okay, problems with the integrity of the and what is the way to deal with erosion? Dimensioning of pipe of components. Okay, proper dimensioning of pipes and components. And if I already have the system is already installed, is already in place, what is the only other way to deal with erosion? Either change somehow the geometry if you're having it through a choke or something, or to reduce the rate. And that's very problematic, okay? Because if I have too much erosion, the only way, if I cannot change pipe, I cannot change anything, the only way is to reduce the rate, and that I don't like, okay? Because I'm losing production. What else? Corrosion. Corrosion can lead to, again, integrity problems. Well, erosion can also lead to loss in functionality, okay? If you have, and this one also. So how do I deal with corrosion? Material selection. We are looking already at the pattern, right? We're just like doctors. We like to give pills for everything, okay? Corrosion, and we have proper material selection, and we have also corrosion inhibitor. Okay, that they act different ways. Yeah. If you want, yeah, we have one more, right? I almost forgot, which is that you had a guest lecture on Oscar. Oscar, that was what was a big issue after this compressor, subsea compressor, slugging. Okay, slugging is a big issue. Can lead to also increased delta P and can lead to loss in functionality. If you get a separator gets a very big slug, then it at the end it cannot separate. It can lead to vibration, so it can lead also, it can cause actually all the three. Okay, and how do I deal with slugging?
Pressure control.
Pressure?
Pressure control.
Pressure control, that's one way. So I can, there are different ways. They call it, yeah, it's called kind of choke control. You have also gas injection. Okay. But basically, during the design process, the field development process, basically have to look at the dimensioning of pipes. Okay, remember I showed you that the flow pattern depends on the superficial oil velocities, and if you see that that's causing slug flow, then you try to increase one or the other to take it out of the slug flow region. Okay. Otherwise, I have to use choke control, gas injection, or I also have to say use a slug catcher instead of a normal separator of a separator. No chemicals for slug. Okay. And I want to say in the compendium, if you, so I will just encourage you to read through the compendium. I think it's in page, let's see, because we already, you were lucky in the guest lectures. They really discuss some of the things are presented in the compendium. But if you really want to refresh, or you didn't go to that lecture, you can go through it. And yeah, it goes through some of them. It tells you also that figure is interesting to show where, this flow assurance issue, where is it affecting my system. Okay, for example, asphaltenes, you see they can go all the way from reservoir to process, also scale. Hydrates usually is when the temperature goes low enough, that is at the top of the well and pipelines and all the way to process. Wax, the same thing. Emulsions can cause trouble everywhere in the except the reservoir. FIV stands for flow induced vibration. Usually it's in the wells, after the wells, pipelines, manifolds. Corrosion is a problem all along. Slugging, well, and pipeline, and erosion can be a problem all along. Okay, so let's take that. I think that's okay, just to give an overview. And here you have the description of some of the problems hydrate. You know that you have to be inside or outside that region. You can change the insulation such that you don't reach into that region. That's the last exercise you're going to have, is going to be related to that. Or you can also change the line by including the inhibitor. Okay, you have slugging. What I told you, you have formation of slug, and here you have slugging. That's riser. Here you have the seabed, and here you have the FPSO. And you have this phenomena in which the liquid starts to accumulate at the lower part, and then pressure of the gas starts increasing, and then all of that bulk of liquid, is flushed and produced to the separator, and that causes a lot of issues. It's called severe slugging. The scale, slightly, the types that we have, how do we treat them? Erosion, what erosion can make on a choke, can really damage the functionality of a choke. Corrosion and wax. You are actually doing an exercise on wax, and here is what we already discussed on emulsion. Okay, so keep that in mind. Wait, getting too big. Now, how do we all of these flow assurance issues that we have somehow, what how do they affect my field development process? We have somehow said here, but I want to make it a bit more, structured. Okay, so let's put here flow assurance considerations during field development. Okay, and the first part where they appear, it's in the early studies. Okay, that's exactly before when you're still evaluating all the field development options that I have. And the main intention there is to find out or to detect and flag possible what we call show stoppers. Okay, something that if I use that particular concept, development concept, that I will have, for sure I will have a problem. Okay, and these typically are the big guys that I have limited ways to deal with them. That's slugging. Okay, that's hydrate. Okay, and that's usually wax. Usually look at these three. Okay, for long transportation distances, for example, I'm looking at the 40 kilometers pipe to develop that field, and I know, well, the fluid will cool down, so I will need either to inject inhibitor or I need to perform pigging. Is something that is a showstopper. That due to that problem that I don't have a way to solve it, I cannot produce. Maybe slugging, I will have very big slugs, and then I need a slug catcher. I cannot put that on an FPSO, for example. These type of things. Okay. Then after that, the next part where it appears is in the feed. Okay, what feed stands for? Nearing design. Okay, and it appears here by making. Here I already have a specific alternative, development alternative selected. Okay, and then you can go in detail to make your study about, you say, all your hydrate management plan. Okay, if it's going to be temperature, insulation, if it's going to be heat tracing, if it's going to be chemical injection, you do the same. If you have to deal with wax, you do the same. If you have to deal with scale, okay, you design your management plan, how you're going to design it. Okay, and here most important is that you have to start making prediction of temperature and pressure and velocities in the production system. Oh, she's okay. Okay, especially in pipelines, flow lines, equipment. Okay. Okay, and I have to find here something important I want to mention is okay, like this picture I want to bring your attention. You have to it's called dead legs or cold spots. Okay. Like if you remember that figure we had, okay, the well is actually entering through here, the well stream. Then it can go either to this header or to that header, right? Let's say that we are producing through that header. So the thing here is that if that valve is closed, that's a crossover valve, all of these piece of pipe from here to here, it will be actually no flow, okay?
So you will have that the fluid in this region, it will cool down. And then you might have problems that you have hydrate, and you might have wax, or you might have all kind of issues here. So that's analyzing all of those, that we call it a dead leg, okay, to see what problems, where are my dead legs in my system, okay.
So does feed only include, say, running simulations and doing calculations?
Yeah, we're going to talk about that just now. Just okay, and then we have the APC, where we still have to see engineering, procurement, and construction, where we still have to define all of these. But the main strategy to deal with my flow assurance issues is defined during the PDO part of it, and during the feed you define the dimension, and you kind of fine tune all the details of your plan. Okay. So now we talk about the tools. Okay, so here I'm going to put here, that's a dead leg. Okay, that is a cold spot during production, and I have to be sure I don't get any hydrates, I don't get any plugging, because otherwise, then if I want to operate that part in the future, let's say, then I might have problems with that. Okay, so now we talk a bit about what kind of engineering analysis, engineering tools used, or let's say commonly employed. Okay, so we use a multiphase flow simulator, okay, to predict basically pressure and temperature along the pipe. Okay, and that's, you are having an exercise on wax, on you're using Excel, you're using basically that. Okay, and for that we can use any kind of simulator. You can use your own tools. You can use there are some others that are called GAP, pipe sim. You can use you want also to look at the you can use a transient flow simulator, that the other guest lecture we had, like for example Olga or Leda flow. Okay, and that's more for look at the startup, shutdown operations, and also when you have slugging, when you have transient phenomena. So you first P and T, you see where you might go inside the hydrate region. You can see the effect of insulation. You can see the effect of heating on a normal multi-phase flow simulator. You can use also HYSYS. Okay, we didn't use it so much. We didn't use it at all in this course. And transient, this is more for slugging, shut-in, and startup. Okay. Other things that we make that are extremely important are also here you use for erosion, for example, to verify the velocities in the pipe. Other thing are PVT and lab test. Okay, and that you make to calculate, to estimate hydrate, wax, scale. You can also make emulsion test. Okay, that you have covered a bit in the. Sometimes we can also make erosion. Erosion, if you suspect that you will have erosion through certain component, like a valve, for example, you can also make test it for a period of time to see how much erosion you get. Then we have you can use CFD. Okay, that CFD stands for computational fluid dynamics. Has any of you worked with CFD before? No? Basically, everything that we are doing now so far is one-dimensional, right? We are doing along the pipe, and we are, doing just our calculations along the pipe. CFD allows you to look at the 3D geometry. Okay, if you want to see what happens with the geometry inside a valve, how can you improve? For example, you're getting a lot of erosion. let's say you have a bend like that, okay, very sharp, and you're getting a lot of erosion in that part, you can use CFD really to help you to say, well, I should make that bend in a different way, in a different way which is less prone to erosion, okay, or different components. And then you have FEA, that stands for Finite Element Analysis. Okay, and that's for calculating stresses on structures. And also, of course, we have a lot of standards that they tell me. You have the erosion standard that they tell you how, some recommendations how you should put your system. Okay, that clear? That's more or less why is it important? And actually, there are quite a few things that are very important. Okay, if you have hydrate, you have to have this chemical management strategy. If you have wax, you have to have how to make pigging in place becomes very important, and that can really change dramatically the cost. If you have slugging, you say, well, I need a slug catcher, or I need to find a way how to operate outside the region. So it's something that really impacts the cost of our field. I want to show just a figure on like all the chemicals that we inject. That's for Erosion, okay, all the kind of chemicals that they are injecting. And this hammer, it's inhibitor, okay, so you have scale inhibitor A that you put in the produced water and you make it continuously. A scale inhibitor B, it tells you the concentration that you have to use, that you have to put in the seawater and you have to do it continuously. Corrosion inhibitor, continuously. Emulsion breaker or demulsifier, you have to do it continuously. Foam, okay, you have like emulsion that is liquid inside the liquid, you have foam which is gas inside the liquid, also you have to inject. Flocculant to improve separation. Wax inhibitor, biocide, you have bacteria, oxygen to avoid corrosion, H2S, MEG, okay. And here you have, so what am I injecting in the well? It's actually only it's only the hydrate inhibitor, okay, nothing else. I don't need anything else. Luckily, I don't need anything else in the well. All the others are in looks like they are on the platform. And I just want to very quickly, okay, what else did I have? Okay, very quickly to talk about the distribution system when I want to distribute all of those chemicals to the wells. Okay, for example, like in that case, that's Neuer, and I have to distribute to send some chemicals, scale inhibitor, hydrate inhibitor to those wells. I usually use the umbilical, okay, to send that. So the umbilical, like you probably cover some other course, has many different things. Power cable, if I have to power, I have signals, I have hydraulic to actuate all the valves. But inside that umbilical, I also have the lines for the chemicals that I need to inject. Okay, like scale, so that also affects the cost. So let me copy that and put it here. You have some figures. It looked like you had a guest lecture and you didn't. Very sad. Okay, so in that case, you see you have many other things, but you have power cables, high voltage, you have fiber optics transmitting signals, and you have hydraulic lines, and you have the chemicals hydrate inhibitor. And I can add a lot of things depending on what I need on my well. So here you have another example, but how that umbilical, so usually is connected to a unit that looks like that. It's a subsea unit. Uh, I think I had a figure, but maybe not. Let me check.
What is the diameter of this?
Yeah, it might not be very something between this and this. Depends on what you are transporting. Okay, that's the unit, how it looks like. And the unit, the only purpose of, let me take, we can take a snapshot of that. Wait. Is to take that umbilical, because that comes in one big cable, okay, in one big chunk. We put it next to it. Okay, that was one unit. If you were walking, I think they don't have it there anymore, but if you're walking in close to Statoil in root wall, they have it. And you can take a picture if you, just kidding. I did it properly. I did a visit and then we took a picture. Okay, but basically you have the umbilical, which comes with all of these different things, and then you have this unit in which you have a manifold that you distribute to all the different wells. So then from the wells you can have either separate lines if they are very close, like in the case of Neuer, they are very close, so you have one line for each one, or you can have another umbilical going to each one of the wells. Okay, because you have to distribute at the end. They come from the platform down subsea. In, let me take again the figure of Neuer or Neuer. Okay, you have one. I think there are these two that come down. You have the subsea distribution unit. In this case, you have two, and then they give to all the wells as subsea. Okay, and that's how the system. If you go even further, we go to each one of the. As just that you're aware, we are not talking about subsea. For that, you have a whole different course. But just to be aware, the consequences. So that's why you have to know your fluid. What do you expect? Because otherwise, you are making big changes on the system. Like this is that after the umbilical comes to the if you have a, in this case, yeah, after the umbilical comes to the well, then you have to have some ports in which you transfer, and inside the Christmas tree, or inside the well template, you have a line. For example, in this case, you have scale and you have methanol inhibitor, okay, for injection on the well stream.
So during the injection of these inhibitors, the gas stream is closed, like the production stream?
No, it has to be, otherwise you get hydrates, so it has to be continuous. So that's why you see here you have, for example, in the case, maybe methanol here, they don't need it all the time. They just need it on demand basis. And here you have a choke to control the rate. Okay. Remember that you have a single conduit, okay, that comes at a very high pressure. So the only way to control the rate is if you have a control choke in each well. Okay, so you can control how much you're producing. But here you have a check valve, for example, on the scale, so such that you don't get backflow. Yeah, so going back to our figure, now we can explain, or I can explain, or you can understand, okay, why you see here you have not only the well stream, but you have a lot of connectors around. You have a lot of lines. So these are all the lines that you need, the hydraulic line, the chemical inhibitor, all kind of things that go and connect to the well. Okay, so let's see what else I have before we finish. Okay, so that's how the connector looks like. Okay, if you that carries different things on the well. It's a multi-bore connector. Okay, that I use to transfer not only the main fluid stream, but I also use it to transfer the hydraulic liquid, the lines, whatever I need. Yes. Yeah, I'm not sure if yeah, maybe I can just take a quick
So temperature, we are not going to talk too much in this course, okay? Because we are talking mainly what affects the production rate, which is pressure, okay? And I explained more or less, I hope you understand well enough, how do we compute rates, equilibrium rates, what affects my equilibrium rate. Temperature is important in the case of flow assurance, okay? To know if when you're going to have hydrate, when you're going to have wax, mainly for that purpose is important temperature. And temperature calculations basically um, based on actually the energy conservation equation, okay? Okay, if we take the same equation we had the first law of the thermodynamics for open systems, but now we make our system extremely small, just like a piece of pipe, we get the differential expression that dq over dl equal to a mass flow times d enthalpy over dl plus the sine of theta times g. Theta is the inclination angle, and v dv over dl. Okay, that's the equation we get. And now the problem is to find from there. Remember, h is a function of temperature, okay, and can be also a function of pressure. But that depends on the fluid you have. If it's a gas, if liquid, okay, h is Cp times dt dH, right? But if it's gas, then dH equal to plus, let me see exactly how did I write it. Sorry, the Joule-Thomson coefficient, I put it directly like that, times dP times dP. Okay, and this part is relatively simple to make, and that's the exercise you are making. Okay, just Cp. Sometimes you have to take the variation of temperature also, but when it comes to gas, this part really makes it a bit complicated. Okay, so that's why we don't have time to go through an exercise with gas. But basically, I take that equation and using some simplifications depending on the fluid, I arrive to I have an example here. I think I put an example here. Okay. For liquid, I think that's the equation that you're using. Using the assumptions that what are all the assumptions? Okay, you get to that equation that's the one that you guys are using. And we have different development for gas, we have different development for multiphase flow, but we don't have time to cover all of them. But just to make you aware, liquid is really the only one where we can have an explicit expression. For gas, it becomes implicit, and we have to solve the equation in an iterative manner. And here there is something important, that is this A, okay, which I didn't put it here. Oops. Okay, but that's, yeah, A should be, okay, A is M. Okay, A has this heat transfer coefficient. So one part is to find the equation that I'm going to use to calculate temperature and see if I can either solve it implicitly or integrate it along the pipe, or to get an explicit expression. And the other part is to calculate the overall heat transfer coefficient. That means that all the resistance, the thermal resistance that I have to have from the fluid all the way to the ambient. Okay, sometimes I have just the you have, so normally you have forced convection inside. That's what you're calculating in the exercise of wax. You have T of the fluid all the way to T of the wall. That part is forced convection. Okay, this part is conduction. Okay, sometimes you have insulation. That might be conduction also. Okay, and then you have here you have T ambient, and then you have again forced or free convection. Okay, so you have to know exactly what is between the two temperatures you have, the driving temperatures, and with that you calculate your U. And I guess you have taken some courses that they have explained that, right? I don't have to go in detail into it, or I will give you like a small refresher next week. Okay, but basically two things: the energy equation can be very complicated, very simple, and to find out the heat transfer coefficient that you need to go from the fluid temperature to the ambient temperature. Okay, so see you. Thank you for coming this week. See you next week, and yes, I think next week we have a guest lecture, another guest lecture. Okay.